mentioned that geometric dimensioning and tolerancing is a set of symbols and rules that allow manufacturers, designers, and inspectors to speak the same language. One way it delivers this information on the drawing is by the use of what's called a feature control frame. These feature control frames contain GD&T symbols as well as other information that helps us define the requirements of the referenced feature. As we said, the feature control frame, or FCF for short, is the method to communicate GD&T in a drawing. A feature control frame can reference a single feature, multiple features, or patterns of features. It outlines the geometric controls being applied and the requirements that must be met in order to be within tolerance. Notice this feature control frame here that is directly attached to the size dimension of this hole. The geometric tolerance for this hole is contained within the components of this feature control frame. It tells us the shape and size of the tolerance zone and any unique situations that are applicable. It also tells us what other features this hole is in reference to. Now, this lesson is not going to teach you everything about all of the symbols. We're just going to show you how they are applied on a drawing in order to convey different information. So let's break down the components of a feature control frame so we can begin to understand the controls and how they're applied to that feature. First up is the leader arrow. This arrow points to the feature that the feature control frame is directly associated with. This arrow can also be replaced by an extension line or omitted entirely depending on the feature and how it's controlled. But don't worry about those situations now. We'll cover those later in this lesson. Next, we see the geometric symbol. This is the portion of the feature control frame that you will see one of the 14 GD&T symbols. This symbol carries its own set of rules and interpretations, again, that we'll cover later, more in depth in the rest of this course. After the geometric symbol, we see this diameter symbol here. Now, this diameter symbol is not required for all feature control frames. In fact, it's only used for feature control frames that utilize a cylindrical tolerance zone. This is the portion of the feature control frame that's going to describe the shape of the tolerance zone. We'll cover this topic more in depth again within each lesson. Now, every feature control frame will contain the tolerance value. This value in the feature control frame is the total amount of tolerance given for that feature. The unit of measure is never listed on the feature control frame, and it's usually based on the drawing standard used for that specific drawing. We also like to point out here that the units used in a drawing do not affect how you interpret GD&T. So whether you use inches or millimeters on your drawing, the interpretation throughout this course will not change. If it's easier, just imagine the units that you are comfortable with. Next up, if applicable, we'll see any feature of size modifiers. The feature of size modifiers like MMC or LMC will be applied in this location. The next section of the feature control frame will contain the primary datum feature reference, if required by that geometric control. Next, we will see the secondary datum feature reference, and then the tertiary datum feature reference. Again, these may or may not be required depending on the symbol being used. These components, when combined together, can give us all the information we need to interpret the tolerances applied to this feature. In fact, the feature control frame can be read from left to right, much like a simple sentence. Let's break this example down into words from left to right using the individual components we previously outlined. This feature has position of 0.2 diameter tolerance at maximum material condition in reference to datum features A, B, and C. It's helpful to remember that every feature control frame can be broken down into simple words. This helps us begin to interpret the geometric control and how it's being applied. One very important concept to understand when interpreting feature control frames is whether the feature control frame is being applied to a feature of size or a surface feature. However, to understand this, we must first understand what a surface feature is and compare that to a feature of size. Now, let's imagine a part like this clevis bracket. We know this is comprised of tangible surfaces, right? We've highlighted a few of these surfaces for you. Surfaces can be flat surfaces, curved surfaces, or even cylindrical surfaces. Imagine zooming in on a surface, and it's composed of thousands of small elements that, when viewed together, create this one constant surface. By controlling this surface, we'd be ensuring that all of those individual elements of that surface are within a defined tolerance zone. When a surface is being controlled with a feature control frame, it's saying the individual elements of that surface are being checked. So what is a feature of size then? Well, features of size are comprised of surfaces. They can be made of opposing surfaces or continuously revolved surfaces, like in the case of a cylinder. The standard defines a feature of size as one cylindrical surface or a set of two opposed parallel elements, each of which is associated with a directly tolerant size dimension. When a feature of size is being controlled with a geometric symbol, that geometric control is now directly controlling what's called the central elements of that feature of size. We're no longer directly controlling those surface elements we were talking about when we were controlling surfaces. So what is a central element? See in these examples that there's a midplane or an axis created by the surfaces of the feature of size. The geometric symbol and the tolerance zone being applied to these features of size will be controlling these central elements as opposed to the individual elements of that surface. According to the standard, these central elements are perfectly flat and perfectly straight. So for a midplane, you'd have a perfectly flat plane. And for an axis, you'd have a perfectly straight axis, even though our features, the cylinders or the width features, will likely be imperfect. We will cover how to create these perfect midplanes and axes later in a different lesson.